So we are discussing our central force motion chapter, and we talked about how the central force is actually a force that depends on the radial distance. Okay, and we also said that the central force is responsible for maintaining orbits. The orbits can be circular, the orbits can be elliptical, whatever. So now our main aim is to find r as a function of theta. Now, what is this r as a function of theta? Okay. So consider this is the sun, and say the earth here moves with an elliptical orbit around the sun. Okay. If now this is the radial vector r, okay, r is a radial vector from the sun to the earth. So here I draw my earth here. Okay. Now, if I can find, so what happens when earth moves? So when earth moves here, it traces out a particular angle. Now, if I can find what will be r as a function of theta, that means if I go from here to here by covering a particular angle theta, if I can get the value of the length of r, suppose I go a little bit more to theta dash, a greater angle, and suppose I can find the length of radius vector r. In this manner, for various angle theta, if I can calculate the length of my radius vector r, then I can easily say what is the orbit that the earth is in which the earth is moving. Agreed. So this is same like, so when you have this say coordinate system, so when y and x, okay, and consider you have a circle. So if you know y is a function of x, then you can easily predict whether it's a circle or not. Remember what was the equation of a circle? For a circle we have x square plus y square equals to r square. Okay, this happens when you shift the origin from this place and you bring the origin to the center of the circle. In this case, this is the equation of the circle. Now you see y can be written as a function of x. How? Look at this expression. From the same expression, a little bit of algebraic manipulation gives me root over of r square minus x square. Agreed? So what does this mean? This means that if I know y is a function of x, then I can easily predict what type of diagram I will have on the xy plane. Similarly, if I can find the equation that tells me what will be the r in terms of theta, then I can easily predict the orbit around which the planet is moving. So that's my target. Okay, so I hope you understand why we are trying to find r as a function of theta. Now question is how, and so the question is how we can proceed, what to do. Okay, so now you have to understand something very interesting. One is we will approach the energy. We will take the energy approach and we will try to solve the central force motion. So let us take the energy approach. So consider the earth is here. So the earth has a linear velocity v, okay, that because of which it is rotating. So the first kinetic energy is the energy due to the linear velocity v. So what is the energy? That is half into m into v square. But you know that linear velocity v can be written as r omega. Okay, so let me remind you what linear velocity v is. We have read that in our circular motion. So remember, if an object is moving around a circle, so consider this is the object moving around the circle, that each point of the circle, the velocity of the object is linear, that is v, and this v is tangential to the circular orbit. So this is the linear velocity, and this linear velocity can be written as r into omega, where r is the radius and omega is the angular velocity. We have already done this in our circular motion chapter, so we are not going to do that. So one thing is clear, that one kinetic energy in this elliptical motion is half m. So what is r? So v square is r square omega square. Agreed? So what is omega? Omega is nothing but theta dot. So let me write in a good form. So r half m r square theta dot square. Agreed? So this is the first kinetic energy. However, there is one more kinetic energy that you have to understand, and that is very subtle. Okay. Now this kinetic energy, you see, there is a motion along the radius. There is some energy. See, whenever there is a motion, there is an energy that creates the motion. In this case, the motion is towards the radius. You see, the radius is changing. The radius is changing with time. Sometimes the radius is big, sometimes the radius is small. So this forces us to talk of another energy in the radial direction. Because the radius is changing, so there should be an energy that causes the change in radius of the orbit. So that kinetic energy is half m. So what is the radius velocity? Radial velocity? Radial velocity is r dot. So that's square. What is r dot? R dot is actually rate of change of radius with time. Okay. See, radial velocity is an interesting property only in case of your elliptical orbit. In circular orbit, is r a function of time? No, r is not a function of time. So dr by dt for the circle is going to be 0 because r is not changing with time. Agreed? So when I'm talking about the magnitude. Okay, forget the direction. I'm talking about the magnitude of r. So the value of r doesn't change because the radius remains same. But in elliptical orbit, the r changes with time. So there must be a kinetic energy in the radial direction. And last, there is a potential energy. So can you tell me what is the potential energy? Of course, it will be G m m by r. It's nothing but the gravitational potential energy. So instead of writing this G m m by r so long, let me write alpha by r. That makes my life easier. So when an object moves in an elliptical orbit, the total energy is sum of both the kinetic energy and the potential energy. Agreed? So the first equation is the total energy. So what is the total energy? Total energy comprises of the energy in the radial direction, that is half m r dot square, plus second we have the energy in the due to the linear velocity, which is half m r square theta dot square, and then I must add the potential, that is v as a function of r. Now there is one more twist. We know that angular momentum L can be written as m r square theta dot. Okay, this is how angular momentum is written, m r square theta dot. We already know this. Okay, because we know we have already studied that angular momentum is what? Mass into velocity into r. Okay, and we know that velocity is r omega, so it becomes m r square omega. We have already studied this in our lectures in classical circular motion, so I'm not going to expand this. So what I want to say here is that this particular term, the second term, can be written in terms of a angular momentum. Now question is, why do I want to write in terms of angular momentum? Because it will make my life easier, because I know that angular momentum is constant with time, it does not change with time. So what is the final expression for my total energy? The final expression for my total energy is the radial kinetic energy, which is half m r dot square, plus then we have this energy because of the linear velocity, but that can be written in terms of angular momentum. So this term will be written as L square by 2 m r square. What is the third expression? Third expression is the potential. So what is the potential? It is minus alpha by r. Okay, so this completes the lecture on the total energy that a planet has when it is moving around the sun. If the planet is moving in elliptical orbit, then there is a radial velocity that gives rise to a radial kinetic energy. This kinetic energy is always there. The second one is due to the linear velocity that is tangential to the orbit. And the third one is the normal gravitational potential, which is minus alpha by r, where alpha is gmm. Okay, I have not taken too much headache. That's why I've written alpha. Okay, so this is the energy equation for the elliptical orbit. Now what to do? So now let me call this equation as equation 1. Okay, there is one more equation that I want you to focus, is the angular momentum equation, where we already studied that the angular momentum, let me use red color, that will be better. So the angular momentum is what? Angular momentum is m r square theta dot. Okay, let this equation be equation number 2, and we'll play with equation 1 and equation 2. Okay, in the next lecture I'll tell you how we can play with these two equation, and just by playing with these two equation I can actually tell you what will be the r as a function of theta. Once I know r as a function of theta, I can tell you all possible orbits that such type of force can give. All possible orbits that such type of force can give. That we'll see in next lecture.